In this video from Chapter 5, we're going to do a couple of basic examples involving varying forces of interest. And the next video will do a more extensive example. So I'll step off, please pause it, copy these into your notes, and then press play and we'll step through it. All right, so in our first example, we have a deposit of capital D dollars made at time 0 years, and we have a simple interest rate of 7% per year acting upon this account. So simple, we haven't seen that for a while, okay? I'd like to calculate the force of interest 1 month after the deposit is made, all right? So I'm trying to convert from simple interest to force of interest. And this is the first time we'll have used the force of interest definition. So to remind you of it, the force of interest is defined to be the derivative of the accumulated value at time t, the derivative with respect to t, divided by the accumulated value at time t. So it's the instantaneous rate of change of the accumulated value divided by the accumulated value. So it is the percentage rate of change of the accumulated value, right? Now, here's the simple interest accumulated value formula. We take our deposit and multiply it by 1 plus 0.07 times t. And what this does is every year, the account adds 7% more of D to the account. So simple interest, remember, is charging that percentage on the initial deposit, not on the accumulated amount, just on the initial deposit every year. Okay. So there's the accumulated value at time t. D is a constant, we just don't know it. T is our variable here. So I can take the derivative of it, which I'll do in this next line. I'm taking the derivative with respect to t of this expression. D is a constant, I drag it out in front. The derivative of 1 is 0, and the derivative of 0.07 times t is just 0.07. So I get 0.07 times d is the derivative of the accumulated value function. So the force of interest then is the derivative on top, 0.07 times d, and then the accumulated value equation or expression in the denominator, d times quantity 1 plus 0.07 times t. The d's cancel, so it was irrelevant what our size of the deposit was in order to calculate the force of interest. So there is the force of interest at any time t. We are looking for the force of interest 1 month after this deposit. Time is measured in years, so 1 month later, we would say is 1/12 of the year. So I'm going to replace t with 1/12, and that cranks out to 0.06959, or 6.59% force of interest. You'll note this is not a constant force of interest, because look, a different value of t would yield a different force of interest. So this is a varying force of interest. All right, in the next example, we wish to know the accumulated value after 4 years. We start with the $1,000 deposited at time 0 years, and our account earns interest via this force of interest expression. For the first 3 years, it's a constant force of interest of 3%. And for the last year, from time 3 to time 4, it is a varying force of interest, 0.08 times t. So, time value diagram of money. Starting at time 0 with $1,000, I'm going to move it 3 years into the future using the constant force of interest. And then this accumulated value of time 3 is going to get pushed the next year forward using the varying force of interest. So it's going to be a 2-stop process. So here's the accumulated value at time 4. I'll first take $1,000 and multiply it by e to the 0.03 times 3 minus 0. That's the constant force of interest accumulated value formula. So that's going to get me through the first 3 years. So this is how much money I have sitting in my bank account at time 3. I'm going to multiply it by the accumulated value factor from moving it from time 3 to 4 using the varying force of interest accumulation formula, right? So that's e raised to the definite integral of 0.08 t from 3 to 4, right? So we move to time 3, and then move to time 4. Sidebar work off to here. I'm going to crank out that definite integral. The antiderivative of 0.08 t is 0.04 t squared. Plugging in 4 and 3 into the t squareds gives me a value of 0.28. So that exponent is actually 0.28, and that cranks out to $1,447.73.